The techniques and the skills that go under the title of electrical circuit analysis are essential to the study or use of any electrical or electronic device or circuit or system. Today, I will describe one technique that can be used to analyze the behavior of an electrical circuit. This is called nodal analysis, and it is the one which we will employ throughout these materials. Let's look first at a circuit, a collection of circuit elements. As shown here, I have 1, 2, 3, 4, 5, 6 elements. An element for these purposes is simply indicated by a box with a pair of terminals. And these 6 elements are interconnected in this circuit with at points which are called nodes. So this is a node. This is a node. This is a node. And this is a node. There are 4 nodes in this circuit. This point is not a node. It is simply an extension of the connection to this element over to the connections of these 2 elements. Most schematic diagrams, circuit diagrams, you will see tend to be drawn in rectilinear form, and I suppose that is a holdover from the days in which these were drawn very carefully by hand in ink on drafting paper, and the draftsman appreciated the right angles and the straight lines. Now, each of these elements, each of these circuit elements, can be described by a terminal pair voltage, which I've called V. V is the voltage drop from the point at which the plus sign appears to the terminal where the minus sign appears, and by an element current, which I've designated here as I. Now, the choice of polarity for the element voltage is essentially arbitrary. But once you have made that choice and specified plus and minus as defining the voltage V, then it is important always to associate the current that goes with that element as being in at the terminal where the positive sign appears. That convention, and it is simply a convention, will be used throughout this instruction, and it is convenient and essential to use because once you settle on that convention, there is no longer any doubt about the form of the current voltage relationship for the element. If you are not consistent in the definition of the current as in at the positive terminal, then you have to ask yourself each time, now what is the voltage current relationship for this particular element? So far in this subject, we have introduced just 2 kinds of elements. One is the resistance, designated by R, or equivalently by the reciprocal of the resistance, which is denoted by the symbol G, and which is called conductance. Now, if we define the voltage and the associated current for the resistor, these have a relationship which is described by Ohm's law. That is, V equals R times I, or inverting that and making use of the conductance, I equals G times V. So one element that we'll be dealing with, represented up here by a box and here by the symbol for a resistance, is in fact the concept of a linear electrical resistance. We've introduced 2 other kinds of elements, both sources, represented by circles. One is a voltage source with the value of that source represented in association with the symbol. And if we define a voltage for this voltage source and an associated current I, the relationship that goes with this is that the voltage V across the terminals is identically equal to capital V for all I. That is, the voltage source says that the voltage between these terminals is constrained to be a fixed number, V, no matter what the current is. The other source we've introduced is a current source, represented this way. And if we define the voltage, associated voltage as V, and the associated current as I, then for this direction of current, for the orientation of the current source implied by this arrow, the constituent relation is I, the terminal current, equals minus capital I. I forgot to put the capital I on here. That goes with the symbol just as the V goes with the voltage source symbol. This symbol means a current is flowing through this device bottom to top of magnitude I, and in terms of this terminal current definition, that is little I equals minus capital I for all V. So those are the three circuit elements that we've introduced so far, and the ones I will make use of in this discussion as we go along. Remember that all of these element representations are idealizations. They are abstractions. You can find a whole variety of physical elements which over some range of voltage or current or temperature will have an Ohm's law relationship, V equals Ri. And you can find devices in the real world, for example, like a storage battery, which has, for moderate currents, currents of a few amperes, one way or the other, has a fixed voltage at its terminals. But if you load that voltage, that storage battery heavily enough, then the voltage will change. It's not, the voltage source representation only holds over a limited domain of currents. You can create in the laboratory circuits which behave over some range of voltages, V, like a current source, but not over a very wide range, and so this also is an idealization. All of these elements are models which to some extent approximate the real world and will serve for the analysis that we're doing here today. In order to apply what is called nodal analysis, I have to define the currents flowing into and out of all of these nodes. What we are applying here is a technique called nodal analysis. And we're going to apply nodal analysis to these four nodes. Now here I've defined as I1, I2, I3, I4, I5, and I6, I have defined the currents in each of these six elements. That is, for each element there is a current I sub n and a voltage V sub n for the nth element, I sub n and V sub n. I'm not going to number all these. It's not necessary for our purposes here. But for each, I've defined a current, an element current. I'm not going to bother to define element voltages. If I did, I would have to be careful with my polarity so that the plus sign was at the terminal where the current entered the element. But the voltages are not necessary at this point for our analysis, so I will leave them off. Nodal analysis is based on the physical principle called Kirchhoff's current law. Kirchhoff's current law can be expressed in a variety of ways. One way is to say that the sum of the currents flowing into a node being the interconnection of circuit elements, the sum of the currents flowing into a node must equal 0. Equivalently, the sum of the currents flowing out of a node must equal 0. In both these representations, you of course have to take account of the signs of the currents. Now, those two representations of Kirchhoff's current law are entirely equivalent, and you can use either one that you please. It helps, however, particularly when you're learning this material for the first time, to choose one or the other and to stick with it throughout. For the purposes of the discussion today, I'm going, in every case, to sum the currents exiting a node. I'm going to take the sum of the currents flowing out of a node and set that equal to 0. That is entirely equivalent to taking the sum of the currents in. All that changes are the signs. But that's the convention I'm going to use throughout. In other words, the sum of the currents out is going to be 0. That's the expression of Kirchhoff's current law that we're employing. Kirchhoff's current law, by the way, is an expression of the fact that for purposes of circuit analysis, charge does not accumulate on any node. Now I'm going to apply Kirchhoff's current law to the circuit that I've sketched here. This is a circuit which, as indicated, has 4 nodes, A, B, C, D. Nodes are places where elements interconnect. And I've defined on here a current, given a current definition to each element current. That is, I1 is the current flowing left to right in this element. I6 is the current flowing down in this element, and so forth. While I need, for the purposes of this analysis, to have definitions for all of those currents, those definitions are entirely arbitrary. That is, everywhere here that I've shown an arrow in a particular direction, I could equally as well have shown it in the other direction. The choice you make for variables in this analysis has nothing to do with the results that you get. You will get what results correspond to the physical behavior of the circuit. So keep in mind that the current directions I've shown are entirely arbitrary. I have not shown voltage definitions for the 6 elements because they turn out not to be necessary in this technique, the technique of nodal analysis. So with these definitions of currents and these 4 nodes, A, B, C, and D, I'm now going to apply Kirchhoff's current law systematically to each node, setting the sum of the currents out equal to 0. Let's begin with node A. There are 1, 2, 3 elements attached to node A, and it turns out that the arbitrary choice I made of current directions, I1, I2, and I4, all are flowing out of the node A. So Kirchhoff's current law at that node requires simply that I1, the current out through this element, plus I2, the current out through this element, plus I4, the current out through this element, sum to 0. If we move over to node B, in this case, not all of the arbitrary definitions I've assigned to element currents are flowing out, so we have to be careful and take account of the signs. The current flowing out of node B through this element is minus I1. I've defined I1 as positive into the node, so the current out associated with this element is minus I1. I5 is defined as out of the node, so it's plus I5. And I6 is defined as positive out of the node, so it's plus I6 equals 0. Node C, this node, taking account of the polarities, turns out that all 3 of these arbitrarily directed currents, arbitrarily defined directions of currents, are into the node. So summing them up, starting here and just working around the node, it's minus I2. That's the current flowing in through this element, flowing out through this element, minus I5, the current flowing out through this element, minus I3, the current flowing out through this element, and that has to equal 0. Now it turns out that those 3 equations are sufficient to our purposes. There are 4 nodes in the circuit, and the 4th node equation, which I will write in a moment, turns out to be redundant. If you have a circuit with n nodes, you need only write n minus 1 node equations. The nth node equation is redundant and can be obtained by algebraic operations on the others. But let's see how it goes. On node D, just proceeding in the straightforward manner, summing the currents out. The current out through this element is minus I4. The current out through this element is plus I3. The arrow here being in the direction which corresponds to a current out. And the current out through this element, note the arrow pointing the other way, is minus I6. And that equals 0. Now, to demonstrate that this fourth equation, or more precisely that any one of these four equations is redundant, let me add up the first three and show that it yields the fourth. If you look at these equations and look for corresponding terms, you find that I1 appears in 2. So when I add all of these equations, I'm just adding these row by row. When I add them, I1 and minus I1 add to 0. Plus I2 and minus I2 add to 0. I4 appears only once in these equations. So the sum, I'm going to write down here, this is the sum of A, B, and C. Has the first term in it is I4. It appears only once. I5 appears twice with opposite signs, so it drops out when I do the sum. I6 appears only once and with a plus sign, so adding them up I get plus I6. And now we've taken care of I2 and I5. They cancel out. I3 appears only once in these equations, and so it's minus I3, and that must equal 0. The sum of these three equations yields this one, I4 plus I6 minus I3 equals 0. And that, as you see, is the same as the equation on D if I multiply by minus 1. If I multiply D by minus 1, I get I4 minus I3 plus I6 equals 0, and that's the equation we got by summing the first three. That applies in general to any network of any number of nodes with two terminal elements. You simply add up the node currents at all the nodes but one, set some of those currents equal to 0, and that set of Kirchhoff's current law equations suffices to describe entirely the behavior of this network under the nodal analysis technique. Let's apply it now to a specific example. Here's a circuit which has 1, 2, 3, 4, 5, 6 resistors in it, and I've shown the resistances here not as R's but as G's, as conductances. The reason for that will be clear in a moment. So G1 equals 1 over R1, the resistance of this element, and so forth. This network contains two sources, a voltage source of value V1 here, just V would suffice, I don't need the subscript really, and a current source polarized in this direction of value I. The polarization, of course, of the voltage source and the current source are important, and they have to be indicated on the diagram. Now, what have we got here? 1, 2, 3, 4, 5 nodes. This example has 5 nodes. How are we going to proceed? I'm going to sum up the currents at some of these nodes, but I'm going to express the currents not as variables indicated on the resistances or the sources, but I'm going to express the currents in terms of the current voltage characteristics of each of these elements. So in order to do that, I've got to define voltages. There are a variety of ways one can define the voltages in this network. And the optimum way, the way that works in nodal analysis, is to define all of those voltages with respect to a reference node, an arbitrarily chosen reference node. this is a little like measuring your height. If you're standing on a floor and you give someone a meter stick or a yardstick and say, okay, tell me how tall I am, one could do that in a variety of ways. You could measure the height of the distance between your head and the ceiling, and the distance between your feet and your ceiling, and the ceiling, and subtract. Or you could measure the height of your head from the floor and recognize that your feet are on the floor, and that therefore is equivalently 0, or the reference height, and just the measurement from your head is all that it takes. Now, in this network, I could choose any of these 5 nodes as a reference node and say that at that node, by definition, arbitrarily, the voltage is 0. Then we define voltages at all the other nodes. These become node to reference voltages. And with those voltages in hand, we proceed to express the currents out of each node in terms of the voltages and the element definitions. So I'm going to call this central node the reference node, and I'll indicate it with that symbol. The reference node is indicated in a variety of ways, sometimes shown that way, sometimes shown as a triangle, sometimes shown like that. It's referred to as ground. It is simply an indication of the point in the circuit at which we take the reference for all voltages to be 0. And then I'm going to assign node voltages. I'm going to call this node A, and this is the voltage E sub A. This is node B, and this is the voltage E sub B. This is node C, and this is the voltage E sub C. And this is node D, and this is the voltage E sub D. Now, what do I mean by the voltage E sub A? I mean that the voltage at this point, measured with respect to the reference node, is E sub A volts. The voltage at this point, measured with respect to the reference node, is E sub B volts. E sub A is what you would measure if you put a pair of voltmeter terminals in with the positive terminal on that node and the negative terminal on this reference node. With these node to reference voltages, these 4 node to reference voltages, if we know them, we have described the entire behavior of the network. Because if I know voltage E sub A and E sub B, I can take E sub A and subtract E sub B. That is the voltage across this conductance G4. And if I multiply that voltage difference, E sub A minus E sub B, by the conductance G4, that tells me what the current is in this resistor. And I can do that for the other elements and end up with the description of each element voltage and each element current. And that is what we're seeking. We're seeking a description of the electrical behavior of the circuit, and it is fully expressed by knowing the current through each element and the voltage across each element. There is a great advantage of choosing node to reference voltages, because by doing so, Kirchhoff's voltage law, which says that the sum of the voltages around any closed path in a circuit must equal 0, the algebraic sum of the voltages around a closed path must be 0. Kirchhoff's voltage law is automatically satisfied by these node to reference voltages. Let me give you an example. Suppose I start at node A, walk all the way around this outer loop, coming back to node A, and add up voltage drops element by element. The drop from here to here, from node A to node B, is E sub A minus E sub B. That's the voltage drop from this node to this node. The drop from this node to this node is E sub B minus E sub C. From this node to this node is E sub C minus E sub D. And finally, to close the loop, from node D to node A, it's E sub D minus E sub A. And Kirchhoff's voltage law says that that must be identically zero. This is KVL, Kirchhoff's voltage law. Now, if you look at this equation, it's clear that every node voltage appears twice and appears with opposite signs on those occurrences. So I have plus E sub A here, minus E sub A here, plus E sub B, minus E sub B, plus E sub B, minus E sub C, plus E sub C, likewise for E sub D. So the sum of the left side is identically zero because it contains all the node voltages twice, and they occur with opposite, each node voltage occurs with opposite signs. So Kirchhoff's voltage law is satisfied by this definition of node to reference voltages. And from then on, you can forget about Kirchhoff's voltage law. Well, what does it mean to solve this circuit? We've got 1, 2, 3, 4, 5, 6, 7 elements. I got that right? 1, 2, 3, 4, 5, 6, 8 elements. We have 8 elements in this. And solving the equation, solving the circuit, means determining for each element the voltage across it and the current through it. What do we have to work with? We have we can write 4 Kirchhoff's current law statements, one at each of these nodes. KVL is automatically satisfied. And we have constituent relationships or current voltage relationships for each of the 8 elements. And those relationships, the 2 laws and the Kirchhoff's current law statements and the constituent relations for the elements, serve to provide a sufficient set of equations. Let's see what they look like. I got to redefine the voltages in the node. This is the reference node. This is the voltage E sub A with respect to the reference node. This is E sub B. This is E sub C. And this is E sub D. Now what I'm going to do is write 3 Kirchhoff's current law statements at 4 of these lettered nodes. I can write one at the reference node as well, but it turns out that these 4 suffice. In fact, as we shall see, fewer than 4 suffice. 3 will suffice. Let's start by writing Kirchhoff's current law at node A, taking advantage of the fact that this voltage source constrains that voltage. So E sub A is equal to V1. The voltage source appears between the reference node and E sub A. So this voltage is fixed at the outset. It's not an unknown. I will write Kirchhoff's current law statements at these other 3 nodes and see what we get. In each case, I'm going to use the constituent relation for the element between the nodes to express a current. And I'm going to sum those currents to 0. So starting at node B, I have 3 elements attached, 2 conductances and a current source. Summing the currents out, the current out of node B through G4 is E sub B minus V1, E sub B minus V1 times the conductance G4. The voltage difference multiplied by the conductance gives us the current in this element. That's why I chose to write conductances instead of resistances. Had I used resistances instead, I'd have to write E sub B minus V1 divided by R4. And it's just easier to have it all in the numerator. So this is the current out of node B through G4. The current out of node B through G5 is E sub B minus 0, because the voltage at the reference node by definition is 0, multiplied by G5. And the current out of node B through the current source is just plus I. And KCL says that's 0. Move down to node C. I got 3 elements again. Turns out all these except this central node have 3. But if I start here and sum the current out of node C through the current source is minus I, because the current source definition has the current flowing in. The current out of node C through conductance G6 is just E sub C minus 0, the voltage at this point, the reference node, times G6. And finally, the current out through G3 is E sub C minus E sub D times G3. And that equals 0. And then finally, we'll go over to node D and sum the currents here. 3 conductances, one of them tied to the reference node. So if I start with this one, with G3, the current out of this node through G3 is E sub D minus E sub C times G3, plus the current out through G2, which is E sub D minus 0. You know, I'm showing the 0 in all these cases to emphasize that the voltage here is 0. But as you work these problems, you would just write E sub D times G2, not being concerned with expressing the 0 there. And then finally, E sub D minus E sub A, which equals V1 times G1. So it's E sub D minus V1 times G1 equals 0. Now, what have we got here? Kirchhoff's current law expressed at 3 nodes. I chose not to try and write it on this node because I don't know the current through V1 until the rest of the network has, till the currents elsewhere have been determined. Remember, the definition of a voltage source is that it maintains a specific voltage difference regardless of the current. And if I tried to write Kirchhoff's current law at this node, I'd have to recognize the fact that I can't express the current in this source by a knowledge of the voltage at each end. It depends on the currents that flow in these 3 conductances. So that's why I didn't write it on node A. But here they are for nodes B, C, and D. They are all expressions of Kirchhoff's current law, and they amount to 3 linear equations in 3 variables. The variables being E sub B, E sub C, and E sub D. Those are the 3 unknowns in these 3 equations, and from here on it's just algebra. You turn the crank on a 3x3 matrix and solve for the node voltages E sub B, E sub C, and E sub D. You already know E sub A. E sub A, that's equal to V1. So knowing these voltages allows you now to calculate every current in the network. If I want to know what this current is, for example, call that I sub 5. If I want to know what I sub 5 is, it's simply the voltage difference, EB minus 0. So it's EB, I won't put the 0 in this time, times the conductance G5. And if I want to know what the current I3, defined this way, in element 3 is, it's just the voltage drop across there, E sub D minus E sub C, E sub D minus E sub C times the conductance G3. Now note that I define this current left to right because I was going to write the voltage across the element as a drop from node D to node C, E sub D minus E sub C. Back to keeping the currents and voltages defined consistently. A drop from here to here corresponds, you should draw your current so that it goes from the positive end to the negative end in order to be able to write Ohm's law without a minus sign. So you could do this for all of the currents. We've solved the problem. By solving these equations simultaneously, we get the three unknown node voltages. We know the voltage at node A, E sub A. Knowledge of all the voltages allows us to calculate all the currents, and that's what's called the total solution of the network. It's easy enough to write a node equation on this node. I'm not going to take the time to do it, but if you will write that node equation, and you have to take care of the fact that the current that flows out of this node is the sum of this current and this current. You can write it in terms of these node pair voltages, since you don't know the current and the voltage source immediately. You can write that node equation, and if you do that and look at it closely, you find it is equivalent to the sum of these three. That is, if you just add these three up, as I did back here, if you add those three equations expressed in terms of voltages and conductances, you get an equation which is exactly equivalent to the one that you could write on a reference node. There's no point in writing it because we have enough equations here and enough variables. The 5 nodes that we started with come down to 3 equations because we know the voltage here. There's no point in writing a node equation on that node. And we know that the voltage here is 0. 3 node equations suffice. Let's look at another example. Simpler one. Here I've got 3 conductances, G1, G2, and G3, and 2 voltage sources, V1 and V2. Where to put the reference node? I could put there are here 1, 2, 3, 4 nodes in this circuit. I could choose any one of those 4 as the reference node. However, there is a very considerable advantage in choosing as the reference node the node at which 2 voltage sources connect. The 2 voltage sources connect, and that's this one. So if we make this the reference node, we know immediately that the voltage at this node is minus V1, minus because of the polarity of this source, and we know that the voltage at this node is plus V2 because of the polarity and the value of this source. So instead of having 3 unknown node voltages, unknown with respect to the reference node, we've only got 1, and that's this one. I'll just call it E, no subscript needed. E is the voltage measured with respect to the reference node at the point where the 3 conductances connect. We can write Kirchhoff's current law very easily there. 3 elements, 3 resistances connecting there, 3 conductances, and I will write the currents in each of the 3 and sum them up, starting with the current out of node E, out of this node through G1. It is just E minus V1 times G1. The current out of this node through conductance G3 is E minus V2 times G3. And I got the sign wrong back here. The voltage at this point is minus V1. I'm taking the difference, the voltage drop across G1. It is E minus the voltage at this point. Minus V1 is plus V1. This sign should be a plus. And then finally, the current through G2, which is because I'm connected to the reference node, is simply E times G2. E times G2, and that must equal 0. 1 equation in 1 unknown, turn the crank, find the voltage E, calculate all the currents, the network solution is done. The point to make here is that if you have voltage sources connected to a common node, it is always convenient not necessary, but convenient, to define that common node as the reference node, because that then specifies directly the voltages at two other nodes. And right away, you've eliminated two node voltages. They're no longer unknown. They are specified by the voltage sources. One more example and we're done. This one has two voltage sources, a current source, and three conductances. And I've chosen this specifically to illustrate the technique of dealing with a circuit in which there's more than one voltage source and in which they do not share a common node. That is, if we label nodes here, here's one, here's another, a third, and a fourth. This is not a new node, okay? This is just simply the place at which elements G2, G3, I, and V2 all connect. Be wrong to indicate a node out there. The voltage there is the same as the voltage here. But V2 and V1 do not share a common node. That is, they have neither source has a terminal in common with the other source. How do we deal with it in that case? It's only slightly more difficult than looking at the situation of one in which the voltage sources have a common node. And let's proceed and see how it goes. I can choose a reference node in any of four places. This could be the reference node, this could be the reference node, this could, or this could. I'll put it down here arbitrarily. You understand that these are always arbitrary choices. And name the three node voltages as E sub A, E sub B, and could call this one E sub C, but recognize that because it's got a voltage source tied between it and the reference node, I'll just label the voltage at this point V1. It is not an unknown node voltage. All I've got is two voltages that are unknown. And the interesting thing about this problem is that while I know neither E sub A or E sub B, I know that they are constrained by V2 because V2 appears between these two nodes. In other words, if I write the voltage difference between E sub A and E sub B, I get E sub A minus E sub B equals minus V1, the value of this source. Or equivalently, if I start at this point and just walk around to EB, the voltage E sub A plus the rise through this voltage source, the rise is plus V2, must equal the voltage at this point, E sub B. So these equations, they are the same equation, just expressed two ways, represent the constraint imposed by this voltage source. The constraint imposed by this one is already taken care of by labeling this node V1. So we are left with a situation in which we know neither of these node voltages, but we do know that they're related. And the way to deal with that is to think of everything inside this circle as a single node. In the notes, this construction is referred to as a supernode. But the reason I'm doing it is to emphasize the fact that E sub A and E sub B are not independent. And with that much in hand, let's proceed to write a node equation on E sub B using on this node. Sum the currents out of that node. Well, the current out through G2 is just E sub B minus V1 times G2. The current out through G3 is E sub B times G3. It's E sub B minus 0 times G3. And now I've got to determine the current out of this node here. Well, that current has two components. One is the current that flows into the current source, and the other is the current that flows into the voltage source. And I can express this last current that I've got to put in here to get the sum equal to 0. I can express this current in terms of these two separately. The first component, this component, is just equal to I. So I have to add to these terms plus I. And then I have to add the current here, which flows through voltage source V2 and through conductance G1 back to here. I can write that current in terms of E sub A and V1. It is E sub A minus V1 times G1. And these four terms must equal 0. That's Kirchhoff's current law at this node. I could equally well have done it at this node. I chose this one because it was not tied to the end of the voltage source. And if I had chosen this instead, to write it here instead, I would have had to reach all the way around to here and sum up all three of those currents to determine the current flowing out of node A through the voltage source. The current in the voltage source is whatever it has to be to satisfy the circuit equations. Well, what have we got? Here's an equation in E sub A and E sub B. Here's an equation in E sub A and E sub B. Two equations, two unknowns. Turn the crank on the algebra, and you found both the node voltages, E sub A and E sub B. And as we noted earlier, once you know the node voltages, you know all the currents as well by taking differences and multiplying by conductances. Well, that's the full story on solving circuit equations using nodal analysis. The steps are rather simple. You decide how many nodes there are in the circuit, taking account of voltage sources and recognizing that voltage sources constrain the difference between two nodes. You assign a reference node arbitrarily. Arbitrarily assign a reference node and say that the voltage at that point is 0. Then assign unknowns to all of the nodes at which you do not know the voltage. In this last example, you know the voltage here, so I don't have to assign a variable there. But at these two, I did not know the voltage directly by the construction of the circuit, so I assigned voltages to both. Assign node to reference voltages at all the nodes where you do not know in advance the voltage, and then write Kirchhoff's current law on those nodes. Now, in this case, there were two voltages I didn't know at the outset, but because the voltage source constrains the difference between those two, I only need to write one node equation. It can be written on here or on here, either way. Once you write the necessary number of node equations corresponding to the number of unknown node voltages, then it's simply a matter of turning a crank on the algebra of simultaneous linear equations. Now, all that I've talked about here has been applied to circuits in which we have sources and resistances. We will very soon come to other circuit elements, two-terminal circuit elements, capacitors and inductors, which have different, of course, current voltage relationships. The technique applies in exactly the same way. There is no difference. We will also come to devices which have three terminals, transistors, active devices. And we'll find that they can be modified, they can be modeled by two-terminal elements. The transistor models we will use all can be modeled, all can be comprised of two-terminal elements. So if you know how to solve circuits with two-terminal elements, regardless of the nature of the element, you know how to determine the current and voltage distributions in any arbitrary network. And that's nodal analysis. That's how you find the currents and voltages in a circuit.